All right, I believe we have been talking about work and energy. Rock falling. Just to add a little spice to our traditional box fall. Let's give it some mass M, and it is going to fall a certain distance here, so it started at 30 meters, ended at 10 meters. And we should be able to solve this using the stuff that we've learned from chapter 2. So let's just go ahead and do that. I've got displacement, initial velocity, final velocity, acceleration, and time. What I want to know is the final velocity. All right, so what do we know? It is dropped.
So did it drop to 10 meters above the ground?
I care if I'm ending the problem when it's 10 meters above the ground.
Okay, so the displacement is negative 20 meters
Why?
because it's going down, and I thought possibly J hat would be up.
Why?
Because he said so.
Okay.
Up.
All right, he spoke first, he said up is positive. You don't like it? Then, well, then you're in a switch it around. Oh, that too.
Yeah.
Laugh or cry, the choice is yours. All right, so negative 20 meters, and apparently that's not the one I wanted. Sometimes I wonder if I'm the only one bothered by the fact that it's not dark.
So 10 meters is where I landed, right?
10 meters is when I stopped the problem.
Okay.
So it's technically still moving.
It might be. We went to commercial, we don't know what's going on. Maybe it blew up
If
right
there
after.
were- If there weren't 10 meters there, then technically this place would be 30.
If I was asking about it, what happens when it hits the ground? Yes. All right, we know two other things.
Was it drop? Or
Yes, it dropped.
So it's at initial velocity 0 meters per second.
Plus or minus.
Oh, wait, no,
It's already
no,
not,
yeah,
it's just
no.
0.
All right, next.
What planet is it on?
Let's assume Earth.
So
So
9.7.
Negative 9.8.
So we're trying to find final velocity. Which equation would we use?
Vf squared minus vi squared plus 2 displacement times acceleration.
Yeah, that's the right equation. I'm gonna nitpick that, say it correctly. You had, it's an equation, so there should be an equal sign in there somewhere.
Oh, it's final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Basically memorized it.
All right. One nitpick I could do, when you talk about velocity, you said final velocity squared.
It's supposed to be speed.
I think there's general assumption, and I don't know if you can always get away with it, but general assumption is that when you square a vector, what you're talking about is a dot product. So, in which case, the velocity squared and the speed squared are the same thing. If you can't make the assumption that a vector squared is the dot product, then I can nitpick that, and it's actually speed squared. There is no vector symbol over the VS
Yeah.
or VI. Okay, so plug into that, we get is equal to 0 squared plus 2 times negative 9.8 times negative 20. And we end up with our final speed of,
392.
what is it?
392.
I assume that's v squared. You said 392?
Oh.
19.8 meters per second. And that'll be a negative sign from there,
All right. Again, this is our final speed, the final velocity, because of Robin's fault, negative 19.8 meters per second. Now let's take this idea of energy. While it's falling, what are all the forces acting on it? Oh, question?
Yes. Could you repeat why VF and VI are scalars?
Of when you do a dot products are known as scalar products also, and when we derived this formula, we had VF dot VF, the vector, so the result of that multiplication is a scalar.
Okay.
So it's just the magnitude squared.
But we use it for the vector forms too.
Well, we plugged in speeds into here, so VF, this is our final speed,
Okay.
and then we have to think through and realize it's negative.
Okay.
But we do put in the acceleration and displacement are vectors, so that's why there's a minus sign there and there. Okay, so the question I just asked, what was the question I just
What
asked?
energies?
What's it again?
What?
Force is acting upon the rock.
There we go, yes. What's the force acting on the rock?
There's weight pushing down from the rock, and then there's gravitational force pushing down from the rock, and then there's gravitational force pushing up from the ground.
They're being pushed towards each other?
They're pulled.
There's gravitational force acting on the rock.
Downwards.
Downward.
Down.
Yeah, see, when you say pushing, I'm picturing that there's some
Yeah.
force that's coming in from behind and trying to squeeze them together as opposed to they're being pulled towards each other. It makes a difference to me.
Yeah, I know. It just makes sense in my head.
Like capital letters.
So if the gravitational force, or weight in this case, because it's close enough to the surface of the planet, is that a conservative force or a non-conservative force?
Conservative force, gravitational force, yeah.
Conservative force.
Okay. Yep. I like the confidence there. Yes, it is. You're right.
But not
We're
confident.
not confident.
Yeah, didn't come out.
On the test, you
All right, Robin, conservative or non-conservative?
Conservative.
Like you mean it.
Conservative.
Okay. It's conservative, fool.
Can't even
Ask me
say
now.
it. Okay, Mr. T.
All right, so it's a conservative force, so should we assume about the energy?
It decreases as it goes down.
Ooh,
Or it gets transformed into kinetic energy as it goes down.
so what does that tell you about the total energy?
It's equal. So the energy in kinetic should be equal to the conservative? No.
I'm looking for something far simpler than what people are going for right now.
Potential energy turns into kinetic energy as it goes up, as it goes down. The potential energy turns into kinetic energy as it goes down.
Say it one more time.
Potential energy converts into kinetic energy as it goes down.
Okay, yeah.
But that's,
I was hoping for just energy is conserved.
Oh.
It would have been as simple as that, but yeah, more specifically, we have potential energy being converted into kinetic energy. So if I have some mass here that is falling, so it starts from some initial height and goes to some final height, and the only force acting on it is weight. Well, let's figure out the work being done by the weight. I know that work is force times displacement. Up, positive, or negative?
positive.
Okay.
So weight is going to.
So my force is negative W.
Is that the force diagram?
Yes, that's what, just with that W there, and then we can do the absolutely stunning visual effects there.
Wow.
Oh,
Yeah,
neon.
there's the force diagram. And again, if you look at it just right, you get that three-dimensional look. So the force is negative W. My displacement I know is going to be negative, so what is my displacement?
negative.
It's going down, and I think Robin said up was positive.
Yes, it's a negative displacement.
No, given that's the initial height, that's the final height,
HF minus HI.
HF minus HI.
Yeah.
Oh, that's
Because I know we need a negative number here, and HF is smaller than HI, so that is our displacement. This is conservative work being done. And so I get, oh, and W?
negative. No, it's mass times acceleration due to gravity.
Like you need it.
A mass times acceleration due to gravity, but the g would be negative because we're
I
going.
mean, I already got the negative taken
Okay,
into account
so-
right there. So I have negative mg times hf minus hi. So I have negative mg hf plus mg hi. And that is equal to the conservative work being done. As we talked about last time, that should be equal to the negative change in potential energy. So what I have here is negative mgHF plus mgHI is equal to the negative final potential, negative of final potential minus initial potential energies.
Wait. No, I'm sorry. That was really loud. Continue.
So negative mgh final plus mgh initial is equal to negative u final plus u initial. So this is what the energy relationships get us.
So where did we get that U is F and minus Y?
Delta change is always final minus initial.
Okay. Oh, okay.
And the fact that the conservative work is equal to the negative change in potential energies was pseudo-derived last time.
When you mentioned potential energy, you wrote plus C yesterday.
And that's what we're getting to right now. Yes. So I've got this. Thank you. I have this equation right here. So the question is, what is a formula for U that would satisfy this? What could I use for the formula of U so that this is a true statement?
H plus C. Wait.
So why the plus C? Because that's what I wrote yesterday?
Yeah.
All right, what is the simplest formula for U that would make this a true statement?
GH plus C.
The simplest.
Wait.
Just MGA.
Yeah, just MGH.
Oh.
So if U is equal to MGH, then U final would be MGH final. U initials, MGH initial. That works. If I just took MGH, plugged it in for U, UF, and UI, I would get this. Check. Done. What is another formula besides MGH that would also work? And don't just say plus C. Give me something specific. This gets to the heart of what C is.
It's a constant. So,
I'm looking for something far simpler than what most of you are probably thinking at the moment.
Plus 0.
What?
Plus 0.
Okay. I could do a plus and 0. What else could I do a plus?
yeah.
If we did a number, that would make a difference.
If I did another number, it would make a difference.
Yeah.
Plus K.
So I have negative MGH final plus MGH initial equals negative UF plus UI. And if I let U equal MGH plus something other than 0, we'll just say 1. Let's see if it works. If I plug into here, I get negative MGH final plus 1 plus MGH initial plus 1.
Oh.
Which the ones cancel out.
Yes, they will.
So that,
Because I got the negative 1 and a positive 1. That's the plus C. The plus C is the fact that if some textbooks will say the formula is MGH. It actually is MGH plus any constant you want. And that gives us a lot of power. That means we can decide, because we can always shift everything by a constant. It gives us the ability to make H is equal to 0 wherever we want. Now, some people really like making H is equal to 0 at the ground because it somehow just fits for them. They find that nice and tidy. But you are actually adding just yourself a little bit of extra work if you do that. So over here, let's combine a couple things.
I have another.
Yes?
Could you go back to the previous slide? The previous one. So you wrote delta U, but you wrote negative.
Yes.
Just because it's downward?
No, this negative right here is because as conservative work is being done, you're losing potential energy. Positive conservative work causes a loss in potential energy.
Okay.
It goes back to I know that the total work is equal to the conservative work plus the non-conservative work. I know that the total work is the change in kinetic energy, work energy theorem. The non-conservative work is equal to the change in energy. And so what we're left with is that. If I subtract this from both sides, I get the change in kinetic energy minus the total change in energy is equal to the conservative work. My change in energy is 1 too many. This is the change in potential plus the change in kinetic. Distribute the negative sign. Kinetic energy changes cancel out, and what you're left with is negative delta U is equal to the conservative work. That's where the negative comes from.
Did we do this yet? We probably did.
I remember doing it yesterday, and I think it's the only group I'm doing energy with at the moment. Now, let's solve the same problem using energy. I'm going to go through a couple extra steps that at some point I'm just not going to do anymore, but sort of bringing in the work-energy relationship. I know that the non-conservative work is equal to the change in energy. As the rock falls, what is the non-conservative work being done? Let's go back to that beautiful, absolutely stunning force diagram. What is the non-conservative work that is being done?
But there's none. Unless there's air resistance.
No.
Weight is conservative.
Yes, so therefore,
There's nothing. Wait, no, there can't be nothing. It said energy doesn't get lost out of no reason. Joe distribute. So that's in the ground.
all right, work is force times displacement. So no work is being done if
No forces.
there's actually 3 things that would cause 0 work to be done. That's the second, and the third one,
What did he say?
he said no displacement.
And they're perpendicular.
That's the third one. If any of those conditions are met, there's no work being done. So in this case, since there are no non-conservative forces, There is no non-conservative work being done.
Right.
If you want the formality of it, which I'm sure you do,
No.
this is non-conservative force times the displacement is equal to the final energy minus the initial energy. This is 0 times I really don't care is equal to the energy final minus the energy initial. So there is no work. And what I'm leading towards is if only conservative forces are doing work, then what we end up with here is that the energy initial must equal the energy final. That's the essence. If any conservation law in physics, what you start with is what you end with.
So I just wanted to clarify, but does conservative energy turn into non-conservative energy, or?
The conservative energy is not a thing. There's conservative forces,
Yeah.
conservative work.
Oh, okay. But does conservative work turn into non-conservative work? Is that?
No.
Okay,
Conservative work changes energy from one form to another
okay.
within the same object. Non-conservative work is transferring energy from one object to a different object.
Okay.
The three things that were at play for whether or not, it was no displacement, no
Force.
total force, and what was the third one?
Rithika?
What?
What was the, what was the one that you
Sorry,
said?
didn't mean to throw you off there.
The third one that you said, that was,
They're perpendicular, the displacement and the force.
oh,
The force and
No, I was still trying to. So delta E, you wrote potential energy plus kinetic
Kinetic,
energy.
yes.
That's the same thing as EF minus EI. Would they be equal?
This E and that E are the same.
Okay.
At this time, I'm doing it, I just want the terms of energy. I don't need to do it in terms of potential plus kinetic.
Right.
At this point, I'm just trying to set up this idea that if no non-conservative work is being done, energy initial equals energy final. In other words, energy is conserved, which is what you would expect from